So this is the ball lying on the earth, and I have picked it up. So I am applying the force, which is F external. You can also write it as F applied. That's the same thing. So F external force, so external force does work in taking the body, in taking the ball here, suppose in taking the ball from, so suppose this is this point where the ball was on the ground, let it be O, and let this point be A. So in taking the ball from O to A, against gravitational force. So gravitational force was acting downwards and you were taking this body upward. So F external was in upward direction, whereas the gravitational force, so students, we put this arrow mark over this physical quantity. All of you are aware of it. So F external is upward, displacement is also upward, but gravitational force is downward. So external force is doing the work in taking the ball from the ground to height h. You can call it d, you can call it h, you can call it displacement s. All of them have the same meaning. You can, as a general case, you can call it x also. So external force does the work in taking the ball from O to A against the gravitational force. And this gravitational force is conservative force. So then this work done by the external force gets stored as potential energy of the ball. So that's the point. Now, so this was the first step, and second, F external is removed. At A. So after reaching A point, F external is removed. So what will happen? The ball moves. The ball moves, or the ball moved. The ball moved downwards, gaining kinetic energy and losing potential energy. Exactly the same as kinetic energy. So the amount of kinetic energy gained even in between is equal to the potential energy lost. Therefore, potential energy plus kinetic energy is constant at any point during the path. Or we can also say that change in potential energy plus kinetic energy is zero. There is no change, means there's no change. Why? Because this thing is constant. This thing is constant. So final, this sum will be equals to the initial sum. So that I call mechanical energy. So that is this whole concept about. Now let us understand this in little bit in more detail. What are the other conditions that you have? The other condition is that when you are taking this ball from O to A, then net force on the ball must be 0. So when you are taking the ball from O to A, net force on the ball is supposed to be 0. It means throughout the path, net force is 0 means upward force is equal to downward force. It means F external, of course they are equal and opposite, so their magnitude will be same. So they are supposed to be equal. So negative means that they are in opposite direction. So F net means that F external is equals to gravitational force. Both are same. In other words, we can say that because F is equals to ma, so F net is 0, it means acceleration is 0. It means there is no change in velocity. It means velocity is constant, or velocity was constant when you were taking this ball up. So these are the conditions. Then only whole work done by the external force will get stored as potential energy. So these are the conditions that you are supposed to follow. Now, if we talk in terms of potential energy, so this whole external work is, so how will you write? Work done by the external force, as both the forces are equal. So work done by external force is equals to external force into the displacement, which is height, right? So as this external force and height, they are in same direction, so we can simply multiply their magnitude, because cos 0 is 1, right? Both are in same direction. F external and displacement, both are in same direction. So dot product cos 0, 1. Now I told you that F external is equal to Fg. So what is Fg? Fg is mg. So this is mgh, and that is equals to U, potential energy. Now what about the work done by gravitational force? So I am still talking about point number 1, okay? Means when the ball is moving, we are external force applied in taking the ball from O to A. So what will the gravitational work done? Work done by the gravitational force. So F gravitational into H into the angle between them, that is 90 degree, because this direction angle is 180 degree. So cos 180 is, so students, the displacement was in upward direction and gravitational force was downward, so the angle is 180, cos 180 is -1. And what is Fg? minus mgh. So Fg is mg. So these forces are same, mg. The only thing that here the angle is 0, here the angle between the force and the displacement is 180 degree. So that's equals to minus u. So that's equals to minus u. So it means that external work done by external force is equals to minus of work done by the gravitational force. Now, if I talk about, still I am continuing with this first point only, this when the ball is moving up. What is change in potential energy? So here on the ground, students, it is your choice where you are taking the potential energy as 0. So I am taking the potential energy on the ground as 0. And here, so this is initial point, initial potential energy, and the final potential energy I am writing as F. So what is change in potential energy? That is equals to, change is always final minus initial, and that is equals to potential energy at initial position was 0. I have taken it, and here final was u. So change in potential energy is u. Same, this u, yes, and that is equals to work done by the external force. So work done by the external force is u or delta u. It is the same. So it means that work done by the external force is equals to u, is equals to delta u. And as the work done by the gravitational force is just opposite, so that is so work external is equals to minus wg. So minus wg is equals to delta u, right? So or you can say that wg is equals to minus delta u. Students, you always need to remember this point, that work done by the gravitational force is minus delta u. So that's the whole thing. Now we can write this thing mathematically. How we are going to write this thing mathematically? You can take a snapshot of this, and it's better if you write simultaneously along with me. Now let us write these things mathematically. So we've already written that work done by the external force is equals to mgh, and that is equals to change in potential energy also, that is potential energy also, right? And so this all is when I am taking the ball upwards at height h, and work done by gravitational force is equals to minus mgh, that's equals to minus delta u. Okay. Now if I want to write the gravitational force, okay, so let us find the derivative of the potential energy with respect to h. Let us see what this figure is. Let us find it out. So d by dh of u is equals to mgh. So put the value mgh here. So mg is constant, it will come out. And what is dh by dh? dh by dh is 1. So 1 into mg is mg, right? What is mg equals to, students? Mg is equals to, see this is minus mg and this is mg. So this is the external force and this minus mg is gravitational force. So this mg is your external force. So that's how you define the external force. So if there is minus du by dh, so obviously it will be equals to minus g, and minus g is equals to the gravitational force, so that is equals to Fg, right? So students, this is how we define gravitational force. This is how we define gravitational force. Okay? So this is just simple mathematical way. And what does this negative sign telling you? This negative sign only telling you that this gravitational force is downward. This is what this negative sign telling you. Now, if we take general case of, see students, of course I can write it as function of h because potential energy depends on h. So I can write it as function of h. So whether you write it as function of h or not, it doesn't matter. But yes, it is function of h, potential energy. Now let us take a general case of conservative force. And the motion is in one dimension. So 1D motion, straight line motion. So of course this Fg is conservative force. So now I can rewrite this as general case, students, conservative force. This Fc you can write conservative, that's also alright. Or you can simply write F, because now we will be dealing with conservative force only. So F means conservative force. Okay? So now I can write it as, instead of H, I'm writing it as X. So Fx is equals to minus du by dx. So I have rewritten it. Okay? Instead of H, it can be this direction also, x, along x-axis also, any direction. Okay? So this is conservative force. So what are other conservative forces? So other conservative forces are like Fg, F spring force, F electric force. So these are all conservative forces. So in conservative forces, the work done does not depend on path. The work done by the conservative force does not depend on path. It depends only on final and initial position. And work done by this conservative force is equals to minus delta U. So these are the three things that you need to understand about the conservative force. Okay, good. So this is this conservative force. It can be Fg, it can be spring force, it can be electric force. This force, okay? And this is this. Now, I can rewrite this. So it's the same differential form. I can rewrite this as this. There is no issue with it. This is the same thing. This is another way of writing it. And now I will be integrating both sides. I will be integrating both sides. So students, the important thing is when you are doing integration, what are the limits here that you are going to take? So that depends. So here the limits depends on change in this position, and here change in potential energy. So the limits here is definitely final position to initial position to final position. So the position was initial. So potential energy here units are these limits are supposed to be according to the potential energy. So the potential energy was Ui, and here the potential energy is Uf. Now, what is this equals to? This is the work done by variable force, isn't it? This is the formula of work done by variable force, right? So this force is conservative force I am taking. So this is the work done by the conservative force. So it is very clear that the conservative force varies along with position. Sir, then why are you taking the same conservative force here also minus mg, here also minus mg, here also minus mg? Why are you taking it same when this conservative force, which is gravitational force, depends on h? Why you are not varying it? Because this is the assumption I have taken. It varies, actually it varies, but I have taken an assumption that near to the surface of Earth, G is constant. It is almost constant. So this is the condition I have specially taken for gravitational force. I am assuming the gravitational force as constant force here, and that is why we have written the formula here. F is equals to work done is equals to F dot S. So these two formulas both F dot S, no integration. So this formula is for constant force, okay, and that's equals to Fs cos theta. So I have used this formula only, but here you will be asking that, sir, why are you writing this formula for conservative force? Because upward for gravitational force I am taking the gravitational force as constant, but actually it is varying. This assumption is just an assumption. Actually, if you want, actually Fg varies with height. Yes, it's not same at all these points, it varies. So that is why the conservative force is different. Sir, give me one more example. Okay, this thing we will understand more in the chapter number 8. Okay, we will have a formula. Suppose you have this plus charge and I have one more plus charge, and let me take it negative. It will be better for you to understand. This positive charge and this is negative charge. So positive charge and negative charge, they attract each other. I am taking this negative charge upward against the electric force. So electric force is downward. So this positive charge is attracting this. So attractive force is downward, but the external force is upward. Same is the case here. The earth was pulling the ball downward, but I was taking it upward. Here you can see the formula is that the force is equals to this electric force. Of course, electric will be equal to external if you want to store this in the form of potential energy. And Fe is equals to K constant. It depends on the product of these two charges. So if this is suppose Q1 and this is suppose Q2, so product of the two charges and divided by distance between them. So when you have taken this negative charge from here to here, obviously this distance r has increased. So here it was lesser and now it is more. So more is the distance, less is the force. So you can clearly see that as you are wearing R, yes, you are wearing R, the electric force is different for all the values of R. So clearly states, so I have given you one example also, that this force, this conservative force, as you change the position, this force will change. So that's the conservative force, and that is why this force is variable force. Only we will take the exception only in case of gravitational force. When we'll do it for the electric force, we will use this formula. When we'll do it for the spring force, we'll use for this formula only, not F dot D. Okay, but here for gravitational force, I have taken the formula upward, F dot D, assuming. So, and this assumption is also clearly written in your book also, NCERT, if you see page 120, second column, second paragraph, that let me read it for you. The gravitational force on a ball of mass m is mg. G may be treated as a constant near the Earth's surface. By near, we imply that height h of the ball above the Earth's surface is very small compared to the Earth radius. So the height that you are moving up is very, very small as compared to the radius of the Earth. And this is the reason why we can ignore the variation of g, that is acceleration due to gravity, near the Earth surface. So if you are taking g as constant, because g is very, very less than the radius of Earth, and that is why we are taking g as constant near the surface of Earth. So g means it is h here. So h is very, very less than. So the height, this height is very, very lesser than the radius of the Earth. So that is why we are taking g as constant. And if g is constant, m is already constant. So of course mg will be constant. And that is why gravitational force is constant. And that is why we use the formula upward, F dot D. But here, these charges are point charges. So this R matters a lot. You cannot take this as negligible. Okay? So students, conservative force is a variable force. It depends on the position. Okay? So it varies from position to position. And you know the derivative of, what is derivative of dx, du? U. And what are the limits? uf to ui. And that's equals to uf minus ui. Okay, final position minus initial position. And that's equals to, take the minus common, or okay. Students, we have forgotten the negative sign here. Okay, so there was negative sign. Because I already know the answer, that negative will be there. So where is my negative sign? So I have my negative sign here. This is my negative sign from here to here. And students, this is equals to minus final minus initial delta U. So this is the work done by conservative force. So I have derived this relation again. You already know this formula. This was already written over there, but that was for gravitational force we have done. But now we have done it as a general case for conservative force. Okay, so students, this is the thing that you need to understand. Now further, if you would like to write, but for small distance, very small distance, for very you can also take this force as constant, and you can write the formula as F dot D for very small displacement. So you can write this also as equals to Fx into delta x. So this work done, you can write it, and when you are summing them all, then this will be integration. So you can write it this way also. So student, this is the mathematical way of telling you what's the definition of force. This is the definition, students. I was telling you this is the definition of conservative force. Okay, so the two important points here are that this is the definition of the conservative force, and this is the work done by the conservative force. So these are two very important points, students. This is step number 1, and from this you can directly write this step. This is step number 2, and from this you can directly write this step. So these steps are not needed. So whenever you get this as general case, xi to xf, directly write delta x. So that's the formula for u now. Okay, so here it was u, so direct delta u. You need not to write these two steps. Not these steps I have written just to help you in understanding, because when you will be giving the competitive exams, you need speed. So you need to do these calculations in your mind. So obviously du, so uf minus uv, that is uf minus ui, that is delta u. So you need not to write these steps, and this step also is not needed. So this step, and of course I can write it as f of x dx, so means integrating both sides with dx. So dx here and dx, it will be no more, only du. So this step, and then this step, and then directly this step. So these three steps are highly important for you in physics. So I have explained the concept of conservative force and work done by conservative force again. Now we have already done the concept of this concept when the ball was moving down. So when the ball was coming down, when F external was removed and the ball coming down, so I've discussed with you that, see, this is the case for any conservative force. This is the case for any conservative force, not only with this gravitational force also. Suppose here, let us take this case of electric force. I have taken this charge, negative charge, from here to here. Now remove the external force, leave this charge here. So here it has potential energy, so it will again be attracted towards the positive charge due to the electric force. So here it will start from rest, and its potential energy will be converted into kinetic energy. So always remember, the job of conservative force is to reduce the potential energy. This is what the so work done is negative, right? So work done is negative. What is the why the work done is negative? Because force and displacements are in opposite direction. So the job of the conservative force is to reduce. When you leave the external force, conservative force will act to reduce the potential energy, and the potential energy will change into kinetic energy such that the sum of potential energy and kinetic energy will be constant. That is, the change in, so if something is constant, students, there is no change in it. So how much is the change? It is constant. So how much is the change? 0. So this we will need in chapter number 7 also. This very simple thing, that if anything is constant, the change in it is 0. Okay? Fine. So that's the concept of conservation of mechanical energy. This concept we call conservation of mechanical energy. I hope you have understood it clearly. Conservation of mechanical energy. Now, as this, if you would like to prove it mathematically, so that was just mathematical proof of this you want. So let us again take a one-dimensional motion, and we have the conservative force applied on an object. So this conservative, so students, I am telling you, forget the external force. It's all about conservative force now. We are studying conservative force. So F means conservative force, okay? So I am not going to write here FC, F conservative. No, this is conservative force. And the body undergoes displacement delta x. So delta x is the displacement under the action of conservative force. So according to work energy theorem, what work energy theorem says? It says that change in kinetic energy is equals to the work done. So net work done, total work done by all the forces. Okay. So if force is conservative, then the potential energy, so potential is also a function, yes. What is it function of? It is a function of x. Even force, conservative force is also a function of x. So F is conservative. It means the potential energy function, I can define the potential energy function is equals to this thing. I'm writing it again. This thing I'm writing it again. So minus delta U is equals to Fx delta x, means the work done is, so as this the force is conservative, so the work done by the conservative force is minus delta U, right? So that's what the conservative force means. Now let us add this. So this is the work done, this also the work done. So this is the same, right? Let us compare this first and second. So compare 1 and 2. Their right hand side is same. So of course LHS left hand sides will also be same. The right hand sides are same, so left hand side will also be same, will be same. So it means this side will be same. So we need not to write this, students. Okay, comparing 1 and 2, so this side same, so they will also be same. So it means that delta k is equals to minus delta u. So taking delta u this side, delta k plus delta u is equals to 0. And see, don't say that I have taken the delta common. No, I have not taken the delta common, but this is the way. That's the same thing, that change in k and change in u. So add both of them. The change is the sum of the total change. So that's another way of writing this same thing. Okay, and that is what your mechanical energy is. So we have proved this thing, that u, this means that u plus k is constant, and that is mechanical energy. So mechanical energy is constant. Okay, now so there's no there's no change. It means what? It means initial kinetic energy plus initial potential energy is equals to final kinetic energy plus final potential energy, right? This is what does it mean. And further, you can write it as, so work energy theorem again you will be dealing with, so that's equals to kf minus ki, right? Work done is equals to change in kinetic energy. Okay, so let us write it in terms of this work done. So kf ki will go this side, so let us write it in terms of, so kf minus ki, so ki will go this side and uf will come this side, so that's equals to ui minus uf. So it means, it is clearly telling you that kinetic energy, final kinetic energy is greater than initial kinetic energy, then the uf is lesser. So kinetic energy was lesser and u final will be lesser. So what does this mean? If this is the ball over here, this is the ball. So coming down, so this was kinetic energy here and this is uf here. So kinetic energy, and this is final kinetic energy, this is, so here this thing was 0 and here this thing is 0. So it means the kinetic energy is converted into, it means this energy is converted into this energy. And this again you can write it as minus delta u. So students, all these things mean the same. Okay, so all this is for the conservative force, and I hope it is very much clear to you. So mechanical energy is conserved, so it does not depend, the conservative force does not depends on the path taken, but it depends on the initial and final. So total mechanical energy of the system is conserved if the forces doing work on it are conservative forces. Now let us do one very simple derivation. Means we are deriving the formula for the conservation of mechanical energy. Let us understand it with the help of one example. So we have a ball of mass m, and it is dropped from this cliff this is a building over here, suppose, and this is the cliff. So this ball is dropped from this cliff and this ball is coming down now. Okay. And the height of the cliff is h. So this height is h. And it is dropped. So obviously dropped, u is equals to 0. And in between it will have some velocity, that is h. Velocity at height small h. The ball will be here. So this is height h. So the velocity at height h. And the final velocity before touching the ground. Okay, just before touching the ground. Now, the total mechanical energy of the ball when the height is 0, so let the energy be E naught, mechanical energy. So E is the mechanical energy. So mechanical energy E, symbol E. And here the mechanical energy at this point at height h is EH, and here when it was at capital height, so height is 0, height is h, height is capital H. So these are the mechanical energy. So what is the mechanical energy here? Here it is equals to mgh, kinetic energy plus potential energy. This is what mechanical energy is. So U plus K. What is U here? mgh. What is K here? Half mv square. So velocity is 0. So kinetic energy is 0. So that's equals to mgh. Now, what is the potential energy here? mgh. What is the kinetic energy here? So it has acquired the velocity v at height h. So half m vh square. Now what is the potential energy here? It is almost 0. So I am writing this potential energy plus kinetic energy. Okay, what is kinetic energy here? Half m v f square, right? So we can clearly see that we know that mechanical energy is conserved. So mechanical energy is conserved. We have just proved it. So they will be the same. So it means mgh is equals to half mvf square. So mechanical energy is conserved. So it means, what does this mean? It means that EH is equals to EH is equals to E naught. This is what does it mean. So it means this and these two are equal. So I am taking EH equals to E naught. So this case I am taking here. So what do you get? M will cancel out, and what is final velocity? So Vf is equals to this 2 will go that side, and this is square, so this will be square root. So that's your final velocity, and that is of course the final velocity when you will take the body dropped from height u. You have derived this relation, v square minus u square is equals to 2gh, and v is equals to, so u is 0, so under the root 2gh. So what you have derived from the equation of motion, same thing you have derived by assuming that energy is conserved. So same formula you have derived by assuming, not even assuming, but that's the truth, that mechanical energy is conserved in case of conservative force. And we have applied and see what the relation we have got. The same relation as we get from the equation of the motion. Okay? Now, let us take, so we have taken these two equal. Now I am taking these two. So what will happen? Let us see. What will be the result? if I take EH is equals to EH. So these two will be same then, right? So it means mgh plus half m vh square is equals to mgh. So students, what's common here? Of course, m is, divide both sides with m. What do I get? So, and I can further multiply both sides with 2 also. And so students, this is which two? No, sorry, I'm not taking these two. These two also I can take. There's no problem with it. Okay, but actually I was supposed to take EH okay, I was actually taking the same. That's all right. So what is the mistake that I am doing here? GH is cancelling out GH, because students, this height is H. So this is capital H and this is capital H. Okay, so this was capital H here and this was capital H here. So the net height. So here also you can take this height as net H, capital height. Okay. Now this is your capital H. This this I have written here. So you can write it as this small h and capital H on this side. So this is the capital H. So see, just one symbol we take incorrectly and the whole thing is going to be incorrect. That is why handwriting is very important, first thing. And second thing is, while doing physics, you are supposed to be attentive. You cannot do physics when you are tired, when you are feeling bored, you are feeling lazy. No. Physics need active mind. Okay? And it needs your, it needs your interest. It needs your interest, physics. Okay, students. So now what do I get? This GH. So I'm interested in finding this velocity. So this was the velocity at this point. Now what is the velocity here at VH? So half VH square is equals to this GH will go this side. So G will be common and H minus H. And if I take this half, so this 2 will go this side and this will be equals to, and this can be written as VH is equals to under the root 2G H minus H, and that is perfect. So 2G, what is H minus H? So that's H minus H. So the velocity, so this is the height from where the body starts falling. So that's the height that the body has covered from the fall. So this is this height. So whether the height is H, whether the height is this, so final velocity depends on the height. So I hope this is clear to you, students. So thank you so much for showing so much of patience.